Hello everyone, how are you? How's everything? I hope everything is going well with you and your families, and you're looking forward to the end of the semester, which is going to be next week. So, today I'm going to tell you about a very simple subject which is called sampling. It's simple, but it's very important as we use it a lot in the real life, and it's a concept that after I tell you about it you realize that you actually know it, but you might have not looked at it this way, from this point of view. Look, the let me tell you about let me start with an example. Imagine you're watching a movie, right? And you're pressing the pause button. What will you see? You see picture, right? So whenever you pause the movie, there is a picture, there is a frame. Most of the movies that you watch, they have a frame sequence, like in every second 24 frames are passing in front of your eyes, and you will see it as a continuous thing, but in fact it's not continuous. It's a series of pictures, that 24 pictures every second are creating this video for you, which looks continuous to you. But actually, you can take samples of this video at any moment that you want. One of these pictures are gonna be in front of your eyes. So this this example can give you a general idea that what do we want to cover as a sampling. So the cool thing about sampling is that it will correlate the continuous time and the discrete time, because it will give us the power to represent the continuous time signals in discrete time domain. So, and most of the time dealing with the discrete time signals are much more flexible and preferable than dealing with the continuous. You could see, for example, when you were doing convolution in continuous, in discrete was much more easier than the convolution, right? But it's very important to take enough samples to make sure that you are representing the signal correctly. For example, look at these pictures, okay? If you are sampling at these points that I'm showing, minus 3t, minus 2t, minus 0t, 2t, 3t, okay? If you're sampling only at these points, all of these three signals, they will give you exactly the same samples. So when you want to reconstruct it, you're not going to reconstruct the correct signal, right? Because at these certain points, these signals, they have the same value. But what if I increase the number of my sampling points? For example, make it double. So then I will have a sampling point here. So this sampling point between minus 3t and minus 2t here will have a different value for this signal, different for this signal, and different value for this signal. So if a signal is being sampled, if the number of samples are sufficiently close to each other, okay, then this sample can uniquely represent the original signal. So this is very important. Look, let me tell you something for your general information. For example, just try to compare a voice that you hear from an old, for example, cassette, like, and compare it with an MP3 sound. Those old cassettes, they were using some magnetic strips just to record your voice. Based on the magnitude of your voice, the pattern of these magnets were changing, and you were recording your voice kind of analogically on them. In the first time that you were listening to those cassettes, the quality was very good, but within the time the quality was deteriorated. Actually, once one of my old friends was telling me that the highest quality of a sound that you can imagine belongs to a gramophone disc for the first time that you are listening to that. But the problem is that after listening to that track for several times, that is gonna be affected and it's gonna be ruined. But how about an MP3 file that you have on your phone or on a flash disk? You can listen to that track for 2 million times and nothing will change. Why? Because it's recorded digitally. It's recorded as zeros and ones. But if you want to represent a signal as zeros and ones, you're gonna be able to represent any moment of that signal as zeros and ones, right? So you're gonna need to sample that signal at certain points and then look at the value of that sample at that certain point and use your A to D analog to digital converter and make them digital. Write it as a series of zeros and ones. So now you might have noticed that MP3s, you can say, okay, it's the 128 kilobit per second or 256, for example. So the quality of the MP3 can change too, right? What defines the change in the quality of the MP3 sound? This number of the samples. So the higher number of the samples, the closer the file to the actual sound that you're trying to record and also replay. So the recording digitally will be sampling, replaying it will be reconstructing those signals, right? So the more samples you have, the higher quality that you have. So it means that the ideal case is to make the samples closer to each other. But the drawback is that when the samples are too close to each other, then we need more space to store that file, because the file is going to be bigger. So you need to get to a point, you need to make a compromise to have an acceptable quality and also an acceptable volume for the file. So now here, as it's written here, if a signal is band limited and the samples are taken sufficiently close together in relation to the highest frequency present in the signal, the samples uniquely specify the signal and we can reconstruct it perfectly. This result known as the sampling theorem. So now let me tell you quickly, how do we do the sampling? Look, if you have a random signal, what is the best way to sample it? We need to have some pulses that cut the signal at certain points to be able to know that what is the magnitude of the signal at certain point. Those signals in time domain, those signals are delta t, because delta t is a signal that is, if you remember, is infinity at zero, but it's zero everywhere else. But why do I need it to be infinity? Because we don't know the magnitude of this signal. So it needs to be tall enough to cross-sect this signal at one point. So it needs to have a magnitude of infinity. So if I have a series of them, if I have a delta t and delta t minus 1, delta t minus 2, delta t minus 3 at different points, I will be able to sample the signal. But in time domain, it's gonna look like this. And we call it a periodic impulse train, because these delta t's are, we call them impulse function, right? This is the best way of sampling is impulse train sampling. But the good thing is that this impulse function, this delta t, when we take them in discrete domain, when you look at it, delta n is actually a function with the magnitude of 1, right? Is a function with the magnitude of 1 in discrete domain at any point. So you can multiply this 1 at any point by the signal. The value that you will get gives you the magnitude of the sample at that point. Like delta of 0 will give it's a function that is only 1 at point 0, multiplied by the value of the signal will give you the magnitude of the signal as 0.0. Delta of 1 will give you the delta of n minus 1, basically. Will give you the sample at 0.1. So this is the best way. A train, why do I say a train? Because an impulse train will be a set of impulses with equal distance between them, right? And each of them can take a sample at a certain point. So this p x of t will be multiplied by p of t, which is basically this train, some periodic impulse train, is gonna create this shape, which is some point or some samples that when you connect the dots together, it's going to create your original signal. So this p of t, this periodic impulse train, is called the sampling function. The period is called the sampling period. It's basically the distance between these. And the frequency, fundamental frequency of the pt will be called sampling frequency. So to the sampled function, we show it with x of p of t, is basically x of t times p of t, where this p of t was the impulse train. So you have to show it this way, the sigma from minus infinity to infinity of delta of t minus n t capital. It means this delta t is being repeated with the period of capital T. Exactly what we saw over here, the distance between them are capital T, which is the period, right? So now, why did I say the difference of this in the time, in the continuous time and in the discrete time? Because I wanted to get to this point that if you multiply something in the discrete time by the train of the samples, it's like you are doing a convolution in Fourier domain, right, with the values of 1 at different points. Because if you remember, convolution in time domain will be multiplication in Fourier domain or Laplace domain, and the other way around, multiplication in time domain will be convolution over there. But the good news is that the convolution with an impulse simply shifts the signal, right? So if you have this signal, if you take your signal x of t to the Fourier domain, do the Fourier transform. The Fourier transform and Laplace transform are the same, just instead of s, we put j omega, okay? So imagine this is the Fourier transform of the signal. Then if you convolute it by this series of the impulses, it's each convolution is gonna give you shifts, right? So it's gonna give you a series of these samples multiplied by the inverse of the period, right? Because of this formula here, it's going to be 1 over t, capital T, the sigma of x of j omega minus like k omega s, which are basically these sampling frequency. So this in Fourier domain, this convoluted by this is going to give you this series, this periodic thing here, where the frequency is going to be that sampling frequency, right? This omega m that you see over here is the highest frequency present in that signal that we're trying to sample, because you remember in the theorem we said the frequency has to be higher than the highest frequency possible in the signal. So this, imagine it's omega m is the highest frequency present in the original signal. Omega s here is a sampling frequency. So as you see, whenever this omega s is bigger, it's bigger than 2 times omega m, our pieces, this sequence of the signals are distinct enough that we can actually reconstruct one of them, because imagine one of them is the Fourier transform of the original signal. So we want to be able to reconstruct it. So at the end of the day, we want to filter one and then do the inverse Fourier transform, right, to take it back to the time domain. So we need to be able to distinguish it. If the sampling frequency is not high enough, it means it's less than 2 omega m, this phenomenon might happen, that you see your functions are not separable anymore. So we cannot distinguish the original signal from these functions because the sampling frequency were not big enough. This thing, you remember at the beginning I showed you this? You might get errors in reconstructing. You might reconstruct the signal into a different signal. You might get a wrong signal when you try to reconstruct it. It's like you try to record a voice, but you take the samples too far away from each other. So when you put them back together, it's not going to make any sense. Or for example, instead of having 24 frames per second in a movie, you have 1 frame per second. When you look at it, it's not a movie anymore. There are a bunch of pictures that you're watching them after each other, and they're not going to create emotion for you because they are not close enough to each other to make emotion. So this case is shown here when you look at it in the frequency domain. So the higher the period, the lower the frequency, right? So the smaller the period, the higher the frequency. So this is what you can see, that why do we need to have the frequency to be, the sampling frequency to be high enough. So it has to be 2 times bigger than omega m, where omega m was the fundamental frequency, let's say, if you're doing you remember from the Fourier series where we were finding the fundamental frequency of a signal, right? So it's going to be that frequency. So I told you quickly, how do we reconstruct? Look here, let's see what happens. We do have our signal x of t, right? We're multiplying it by our impulse train, so we will get xp of t, so the signal which is being sampled in the time domain. Then we take the multiplied by th of j omega here, basically. You will get this signal, this sequential signal that you saw in the Fourier domain, okay? Then in order to reconstruct it, we have to apply a filter. What is a filter? A filter would be a band pass filter, something like this, that can only select one sequence here and suppress the other sequences. So this filter can, if we apply it here on this signal that you see over here, can take one of these basically one of these samples, one of these functions that are being repeated. What should be the magnitude of the filter? It has to be t. Why? Because you remember when we were doing this operation here, it was being multiplied by 1 over capital T. So the magnitude of this function in the frequency domain, in the Fourier domain, was multiplied by 1 over T capital, 1 over the period. So our filter must have a gain of capital T, because this T times 1 over T will make it 1. And this omega C, okay, the cutoff frequency, must be between omega m and omega s minus omega m. Why? Because look, it has to sit here, okay? The way that it has to be bigger than omega m, because it needs to be in this region, but it has to be smaller than omega s minus omega m, because we don't want it to hit the next period, right? So we just want to pick one period of this signal. So we'll get this x r of j omega. What is the xr? R means reconstructed. So let's go back to this graph again. Look, this is what you're going to need for your exam as well. This is the sequence that you're going to follow. We'll give you a signal for sampling, okay? And we'll give you the sampling frequency, or you pick up the correct sampling frequency. So you will multiply this signal by the PT, which was the sampling train, right? It will give you XP of T. It will give you the samples basically. Then you take it to the Fourier domain, XP of J omega, okay, this way. So you will have this. This Fourier domain will limit basically your signal between the maximum frequency available over there, omega. Then it's gonna be a sequence of them, right? Because we said that this multiplication here, when it goes to the Fourier domain, is gonna be a sequence of these functions. It's gonna be a periodic thing, because we said that the convolution by the impulse will give us shifts in the unlimited number of shifts. So then this h of j omega is showing our filter here. So in order to reconstruct, we apply a filter with the cutoff frequency omega c, in which cutoff frequency is between omega m and omega s minus omega m, right? Then we will have x r of j omega reconstructed. So simply by applying an inverse transform, Fourier transform, we can take it to the time domain to get xr of t. So this is the reconstructed time domain signal. So we started from the signal in the time domain. We took the samples, and we can do any operation that we want with it while we do the sampling and the stuff. And then we can reconstruct it. It's like we record, okay, and then we play. So with the example that I told you, imagine you're recording with your digital recorder. All these things will happen, and then you play it. So you took the samples, and then you reconstructed the samples. There is something that I want to tell you, which is called the zero order hold. Look, This is exactly what I was telling you about turning a signal into digital. Okay, so in reality, when you take a sample here, we don't go back to zero. Okay, in reality, actually making impulse is not easy, right? To something that happens at zero time to go up and come back. So basically, we take a sample here, so we hold it at this value until we take the next sample. So we hold it on this value, then the next sample, then the next sample. So this like a staircase shape that you will see here, this is the digital format of this curve. So you can imagine now if we increase the sampling rate, so these staircases are gonna be smaller, smaller, so it's gonna be, the shape is gonna be closer and closer to this curvature that we see over here. So this is called zero hold. Why? Because after I took sample, I didn't come back here and go up again. I held it at the value of the sample until the next sample comes, until the next sample comes. So this thing is called zero order hold in sampling. So at the end, I just want to tell you the meaning of one term called aliasing. As we said right now, the sampling rate must be high enough to make sure that we can reconstruct it, right? And for that, we said omega s must be 2 times more than omega m. If omega s is less than 2 omega m, it means that the signal is no longer recoverable by this filtering method that we just showed. So this effect is called aliasing. So basically, if the sampling is not frequent enough, we cannot recover. This is what we talked about it a lot right now. So we cannot reconstruct the signal. So if you look at lecture note 11 on Moodle, it's actually explained, and there are some examples here showing you where the aliasing is happening and what will happen, that we cannot actually reconstruct and recover the signal after the sampling. So thank you very much for listening. It's, as I said, it's a very simple subject. All you need to remember is actually what happened here, that how we took the sampling actually using the impulse train, and this graph. So this is actually the main thing that you need to use. What you take your signal in the time domain to the sampling, take it to the frequency domain, then apply the filter and recover your signal. As simple as that. So the sequence is basically the whole thing that happens during the sampling. Thank you very much for listening. I wish you a beautiful day. Have fun. Take care.